All right, everyone. Niva, Marketing Operations Coordinator at Thermal Analytics and host of today's webinar. Our presenter today is Dr. Zachary Edel. Zach is a Senior Research Engineer at Thermal Analytics, feature owner for the TAITherm battery extension, and a subject matter expert for vehicle electrification modeling. He has many years of research experience developing advanced physics models, performing numerical modeling, and performing experimentation and data analysis. He has worked with various OEMs and Tier 1 suppliers to model battery degradation and BMS design, with a focus on optimizing BMS control strategy. Zach received his PhD in mechanical engineering at Michigan Technological University in 2013. Throughout today's presentation, you may submit questions in the questions box, which we will review at the end. We are also recording this webinar and we'll be sending you the link following this presentation. And with that, Zach, if you're ready, you may begin.
Okay, thanks, Chris. Today I'll be talking about battery thermal runaway with venting and CFD coupling. And I'll be focusing on some of the new advancements that have been made lately. Special thanks to Logan Canal for working on some of this latest research and adding to the ongoing capability development efforts that have been worked by several engineers here at Thermal Analytics. For our agenda, I'll be talking about predicting physical battery temperatures with TAITherm, coupled with Star-CCM Plus using CoTherm, different internal cell heating models and their calibration to test data, intra and intra-cell propagation rate validations, a few case studies showing coupled thermal-CFD simulations used to evaluate pack and module design, as well as a reduced order fluid node approach to approximate CFD cell venting boundary conditions that in both of these approaches use an internal pressure equation solver to predict when a cell starts venting and when it stops venting, fluid flow rates and venting time. And then I'll talk a little bit about future use case studies and case studies that we've done in the past. Thermal runaway can happen when the battery temperature gets too high, either due to external temperatures being driven too high or from a sudden short circuit. And international law prescribes a minimum time of 5 minutes between the start of thermal runaway and for the car to catch fire, or for the thermal runaway event to pose danger to the occupants of the vehicle. So this requires proper thermal management and heat propagation management, both inside the pack and outside the pack. There are two potential causes for thermal runaway. One is when the external temperatures are driven too high. The other is the short circuit causing rapid discharge and large internal heat generation. And some of the reasons for an internal short circuit are when lithium plating causes dendritic formation to puncture the separator, when the separator construction is flawed or too weak, or when it breaks down at high temperatures, or if the electrolyte is contaminated with metal particles. And then there are also mechanical crush or penetration events that can occur. And some of these can be due to excessive voltage, excessive currents, overcharge, or low temperature operation or fast charging at too low of temperatures. We have 3 different internal cell heating models to predict the heat from chemical reactions during thermal runaway. And the elevated temperatures due to hot ambient conditions, I²R heating at shorts, or internal discharge can initiate the thermal runaway process. The models are based on temperature-dependent imposed heating derived from reaction kinetics. And the heat released by these reactions comes from the electrode separator and electrolyte materials. These models use empirical reaction rate data and are used to evaluate risk of cell-to-cell propagation and evaluate runaway mitigation strategies. The runaway models can be used in conjunction with any of the TAITherm battery models. They can include custom heating functions to simulate adverse heating effects such as shorts and hot gas impingement, as well as incorporating other heating scenarios such as rapid charge and discharge, environmental soak conditions, and cell-to-cell propagation of runaway via radiation, convection, and conduction. The first internal cell heating model we have comes from NREL, which is the National Renewable Energy Laboratory. It uses empirical reaction data, such as data taken from calorimetric tests, and computes the rate of heat from exothermic decomposition reactions from 4 different types of reactions and superimposes those heat rates. And those reactions are based on the interaction and breakdown of the solid electrolyte interface, the anode and cathode reactions. We can see here the equations for this model. Uses inputs such as volumetric heat rate. Actually, that's calculated. The inputs include the heat of reaction and then the battery composition and the rate of reaction. These are expressed in terms of activation energy, reaction rate constant, and gas constant. This type of model can be difficult to calibrate, especially when you're trying to get a target total heat rate generated and the onset temperature for thermal runaway. But it does provide a higher fidelity physics model compared to other approaches, and has also been benchmarked against other modeling software and is used elsewhere in industry. We also have a simplified version of this model with a single representative reaction, which uses the same set of equations, only with a single set of input data. And this does reflect some of the approaches taken in literature. So there are a couple variations here which can use this set of equations. We've also implemented a thermal runaway internal cell heating model from Zhao et al., which is a research paper which describes this model in terms of the equations used. This has been implemented directly in TAITherm and breaks up thermal runaway into 2 components: the short circuit that happens when the separator melts, as well as the chemical decomposition reactions inside the cell. Each reaction uses a user-specified energy, a trigger temperature, and a gas release rate. And this model is also discretized to occur on an element level similar to the previous NREL models. This approach is simpler and easier to calibrate than the NREL method, but doesn't have quite as high fidelity if the test data that you have or the input data that you've derived from other sources does support that type of model. However, with the typical amount of data that people have without a cell teardown and calorimetric test, this is easier to calibrate to test data or expected results. This model includes a local trigger heat rate, an equivalent circuit heat rate, a self-discharge heat rate, and a chemical decomposition heat rate. As a validation of these approaches, we have compared this to a journal paper. This slide shows the initialization of the internal heating that generates the amount of heat required to start thermal runaway. The initial temperature is 55 degrees Celsius. We have an ambient of 35 with a heat transfer coefficient of 15. And in the journal paper, 15% of the cell energy was released in 1 second to trigger the thermal runaway event. For the TAITherm model, we have imposed a 3 kilowatt heat rate that is also released in 1 second. And this is pretty close to what was done in the journal paper based on our calculations. We've used a spiral shell element geometry to capture anisotropic conduction through the jelly roll layers, and also to visualize the temperature and heat propagation inside the cell. This cell is actually a slightly different size between our TAITherm model and the journal paper, but we're using it as a qualitative analysis here to verify the model behaves as expected. So here we have the propagation rate inside the cell. The journal paper and the TAITherm thermal model have similar runaway characteristics. There's a slightly different time scale, but what we're looking for here is just that the thermal runaway does propagate element to element as each one heats up and goes into thermal runaway. in a similar fashion between what's showed with other softwares and what's shown with TAITherm. So we see a similar propagation, and this is considered a validation of the intra-cell propagation rate, at least qualitatively for our models. We also have an inter-cell propagation validation where we've taken 3 cells and calibrated the inputs to match a different journal paper. This has a discretized reactive material, internal heating from the chemical reactions as well as the short circuit, convective heat transfer from CFD coupling, multiple time scale solution approach. And in this case, what that means is that the equations are solved with a smaller time step in our pressure and internal heating solvers, and then coupled with the TAITherm thermal model as part of TAITherm at a larger thermal time step to increase runtime. And there's also an internal pressure solver that calculates the mass flow rate and temperature of the venting material of each cell. And this includes conduction through the cell and pack, as well as convection from CFD and radiation from TAITherm. We've done a case study in a module similar to the BMW i3, where there are 12 cells in series with 94 amp hour cells. There's a total of 44,000 elements in this pack. Library convection is used on the outside to represent natural convection. And then we have equivalent circuit cell heating until the runaway occurs. We have heating in bus bars, and then we have the thermal runaway internal heating equations. So to pre-process or precondition the pack, we have an alternating current here shown in blue, which then stops when the cell goes into runaway, and then we have the heat generated inside the cell at an element level. Our CFD coupling approach here is shown for the 3-cell model, but it's the same for any of our geometries. The transient TAITherm thermal model calculates the surface temperatures of the cells, which then get exchanged with a steady state Star-CCM plus CFD model. That model calculates the heat transfer coefficients and fluid temperatures of not only the venting cell, but the surrounding cells. Those get imported back into the TAITherm thermal model, and that's run to predict the cell temperatures until a venting occurs, at which point we trigger the next CFD run and couple the surface temperatures, heat transfer coefficients, and fluid temperatures again. The CoTherm process automation starts with a thermal transient in TAITherm until the venting phenomenon starts, at which point we coupled with a CFD that calculates the heat transfer coefficient and fluid temperatures, which get imported back into TAITherm, which then runs in a standalone approach again until the next cell goes into thermal runaway. So this is faster than CFD only because the TAITherm thermal model runs faster. And once a cell starts or stops venting, we trigger CFD again, and then exchange information with TAITherm, run it by itself again, and then this process continues as each cell starts and stops venting. And this can occur in any order and is fully automated. To calculate the boundary conditions for the CFD model, we have an internal pressure solver based on a research paper by Mao et al. And this determines the fluid velocity, temperature, and duration of venting for each cell. It can be coupled with CFD or used in a standalone model, which I'll talk about later in the presentation. And the CFD can be triggered under 2 conditions. One is a user-specified value, where you're setting the CFD boundary conditions based on these values, but for a user-specified duration. Or you can look at when these pressure or vent velocities go above a certain value or fall below a certain value. Some of the physics behind this is that the pressure solver uses an inner time step, like I described earlier, to improve solution accuracy and runtime. The results are recorded and time averaged for the outer time step in TAITherm. And each inner time step updates the pressure, and that's compared to the venting pressure. And once the pressure inside the cell exceeds the venting pressure, the valve is assumed open, and it stays open until all the mass in the cell has vented, and the velocity is then capped at 0 meters per second. The inputs to this model are typically derived from either test data or data that's been accumulated online. In this case, we're using inputs from the NASA database, and this is calibrated based on the equations shown here. The main inputs are the total energy released, and then the volume and mass of the cell or reacting material. The image on the right here shows a summary of the NASA database where the thickness of the lines represent the amount of data they have. And on the left-hand side of this figure, you can see a number of manufacturers, cell formats, and chemistries. And on the right, you can see the method that was used to initiate the thermal runaway event. So on the top, we have an internal short circuit heater, which is actually implanted in the cell when it's manufactured. That heats up the cell, then melts and causes an internal short circuit. Then the second case here is an external heater, where we just take a cell and wrap it in a heater or put a localized heater on it to trigger thermal runaway. And the last case is a nail penetration event. And the way in which thermal runaway is triggered does influence the propagation rate inside the cell and potentially heat transfer to surrounding cells. So it's important to consider how the cell is triggered when considering a propagation rate evaluation in the pack. Here we see the CFD coupled results. So in the upper right, you can see the heat transfer coefficient and how that evolves over time as the cells start and stop venting. On the lower right, you can see the fluid temperatures. So these are both coupled, similar to what we do in other underhood and underbody studies, but this is kind of replacing that type of analysis for safety in electric and hybrid electric vehicles. On the left, you can see the temperature profile as it propagates through the pack. And as this coupled process runs, the results are aggregated into a single TAITherm model so that they can be post-processed in one model. These animations were exported from the resulting TAITherm model, and these results can also be used to calculate the CFD boundary conditions on the outside of the module or the outside of the pack for heat protection and occupant safety studies. Heat protection studies can include hot gas impingement on surrounding materials, high voltage cables, motors, connections, and other parts. We also have a reduced order approach, which is a fluid node proximity approach, where we've defined fluid nodes over the vents of each cell. And this approach approximates the convection that occurs when a cell vents, similar to what CFD does, but this is a simpler approach that can be calibrated either to test data or to a CFD model or a CFD coupled model. So this is a single transient model that runs in TAITherm by itself. It has a fast runtime and requires minimal inputs that can be calibrated. The heat transfer coefficients and fluid temperatures are modified by TAITherm to represent local heat transfer to the surrounding cells. And the elements close to the vent receive higher values that automatically update when each cells start and stop venting. These are the results from the TAITherm standalone approach. Again, we have heat transfer coefficient in the upper right and fluid temperatures in the lower right, and then the cell temperatures on the left. And what we see here is a similar propagation rate to the CFD coupled approach. However, the cells do fail in a slightly different order due to the dominance of conduction, in this case through the bus bars. This can be calibrated to rectify that difference in a further study. But the important thing is to have the same propagation rate throughout the pack, which is going to give equivalent boundary conditions to the surrounding geometry, particularly for heat protection studies. These plots show the cell temperatures comparing the CFD coupled approach to the standalone approach. You can see they're very similar. And the important things to note are that the two simulation approaches have the same temperature magnitude, time scale, and cell venting times. And this comparison serves as a validation of the reduced order standalone approach when it's properly calibrated to a higher fidelity approach. Here we see the cell temperatures and how they propagate throughout the pack in an animation. The standalone solution can achieve faster runtimes for trade-off studies and sensitivity analyses, and can also be easily calibrated and used then to vary insulation layers, boundaries between cells, external component shielding, and other effects that can be varied in that model with a faster runtime. Even though both solutions are faster than a CFD-only approach, it's very promising to see that TAITherm standalone can outperform a coupled approach in terms of runtime without sacrificing a lot of fidelity in producing the same propagation rate. It may require additional calibration and may need a coupled approach to inform the model parameters. However, runtime is essential for simulating large packs and full vehicles in one model, where designs can be modified to ensure safety, quality, and reliability. In terms of the runtime for the CFD coupled approach that I've described earlier, we're looking at a 97-minute runtime to simulate 1 hour in the simulation, and this is run on 24 processors. The standalone approach also simulates a 1 hour simulation on 24 processors. However, the runtime in this case is only 20 minutes. So that's 5 times real time. Looking a little bit deeper into the internal pressure solver, we can see that the pressure on the left triggers the cell vent opening. The temperatures in the middle are the fluid temperatures, which are inputs to the CFD model or the standalone model. And then on the right-hand side, we have the velocity, which gets integrated to create a step function velocity that's used in the steady state CFD model. We can also output mass flow rate as an alternative. So there are 3 different inputs that could be used as boundary conditions in the CFD model: the pressure, the velocity, or the mass flow rate. And there's simply 3 alternatives that could all be valid, but some may be easier to implement than others. Here we have a vehicle occupant heat protection study. I've included a few more case studies to illustrate what can be done once the propagation rate inside the pack has been estimated or modeled. In this case, we have a module going into thermal runaway underneath the floorboards of an electric vehicle. And we've modeled this with 2 different floor setups. One is without insulation, which just has steel and carpet between the pack and the interior of the cabin. And the other is with insulation, which has carpet, polyurethane foam, and steel. And these are modeled with a multi-layer part, which can easily be changed to introduce more layers, change thicknesses and material properties. And on the right-hand side, we see the cabin floor temperature. Without insulation, it increases to greater than 325 degrees Celsius. whereas with insulation, that temperature is mitigated down to less than 55 degrees Celsius. So it's very important to consider material stack-ups and insulation layers when protecting occupants from this kind of event. Another heat protection study we've done is for high voltage cables. So this slide illustrates two different approaches to this heat protection study. One with the physics both inside and outside the pack included in the same model. This is shown on top. And one with only the pack exterior modeled, which is shown on the bottom. In the second approach, the boundary conditions can be derived from the cell propagation rates and venting results. And by looking at the circled regions on the right-hand figures, we can see that we've achieved very similar results with both different approaches. So this simplification shown on bottom represents a multi-scale approach where we've taken multiple simulations and run a module level simulation to a pack, to the pack exterior, and simply breaking these up can allow you to run smaller models with faster run times to achieve the same results. But either one's valid, and the method on top may be simpler to set up and run in an all-in-one solution. However, which approach is taken simply depends on the constraints of your design study. We also have a high voltage cable heat protection study here, where we've added a heat protective shield in front of that high voltage cable. So this is just one case here where we're simulating the entire pack in the car. And on the left, we see the CFD results. On the top, we have the velocity of the fluids. And on the bottom, we have the temperature of the fluids. And then on the lower right, we can see the high voltage cable temperatures with and without the heat shield protecting them. Without the heat shield, we see temperatures going up above 55 degrees Celsius, whereas with the heat shield, they stay below 30 the entire time. So it's very important to protect all the components surrounding the pack, and this shows a good way to do that with simulation. In conclusion, multiple internal heating correlations are available, including self-discharge. A quasi-transient CFD coupling process has been implemented and optimized to reduce runtime. A reduced order fluid node, heat transfer coefficient, and fluid temperature mapping process has also been implemented to improve runtime and calibration of the model. And internal pressure equations have been implemented to predict the onset of venting, the venting boundary conditions, and this has been integrated into the entire process. The venting boundary conditions can also be calibrated to test data or extrapolated from known sources, and external venting simulations can also be run. Special thanks again to Logan Knoll for making great progress on these new capabilities and leading the model order reduction development. And at this point, I think we can take questions.
All right, thank you, Zach. Yeah, let's get to some questions here. Can this process be used with other CFD software tools?
Yes, we do have this implemented with other CFD software tools. In this case, we've used Star-CCM Plus for most of these case studies, since it is an industry standard, and that's just typically what we use here. We've also done this with OpenFoam and NGIS, and we do have standard processes for coupling with other CFD softwares.
All right, thank you. Next question, can the cell venting pressure equations be used on a module level or pack level?
Yeah, this is something we're looking into right now. Right now, they predict when a cell starts and stops venting. They could also be used on the outside of the module to predict when the burst disk starts venting on the module and going into the canals of the pack. It could potentially also be used for the entire pack to predict the boundary conditions of the pack when it starts venting. However, it is dependent on the cell-to-cell propagation rate. So it's also something that could be useful, however, would probably need to be calibrated to a larger thermal model or a module thermal model. And then those equations could be used on an external heat protection study.
Thank you. One more here. Can these processes be run on HPCs?
Yeah. In this case, we've done these benchmark studies on a personal computer, ran with 24 threads. However, we do support high power computers, so this process could even be sped up further than what we've reported here.
Okay, well, looks like that'll do it for questions. So that will complete today's webinar. We appreciate you all for attending. You will receive a follow-up email this afternoon containing links to download the presentation slides and watch the recorded webinar session. So thank you, Zach, and thank you all. Have a nice day.